Hello everyone. This is the third video on Riemann integral. In first video we studied the concept of upper sum, lower sum, upper integral, lower integral, and the definition of Riemann integral using upper integral and lower integral. We have also seen that a bounded function need not be Riemann integrable. In second video, we studied the contribution of Darbau's theorem to determine integrability conditions. In the present video, we will learn about integrability of continuous and discontinuous bounded functions. Let f be a bounded function and defined on a closed interval ab, and p be a partition of the interval ab in n non-overlapping subintervals xi minus 1 xi of length delta I. Since function is bounded in the whole interval ab, so it will be bounded in these subintervals, and therefore we may take the greatest lower bound and least upper bound of the values of function f in these subinterval mi, small mi, and capital Mi is the least upper bound of f in this interval subinterval xi minus 1 xi, and mi, small mi, is greatest lower bound. We have studied about upper sum and lower sum corresponding to the value of least upper bound, which can be taken corresponding to each subinterval, and the length of each subinterval when multiplied and added we get upper sum. Similarly, we can get lower sum corresponding to the greatest lower bound of the function in each subinterval with multiplied with their distances and adding. So there is a difference of these two, and this difference plays an important role to check the integrability of the function f when function as we have seen that a bounded function may not be Riemann integrable. So in case when a function is bounded, then a difference of upper sum minus lower and lower sum plays an important role. In fact, we want this should be however close. These two terms, upper sum and lower sum, becomes as close as we want. So these are conditions, necessary and sufficient conditions belongings to this difference of upper sum and lower sum for a bounded function that should be Riemann integrable if the difference can be made however small, and there must be a partition for which this upper sum minus lower sum becomes however small. And the next this result is more interesting, that due to Darbau's theorem, and which states that there are infinite many such partition for which function can the difference can be made however small. These two results we have already discussed, and we will use these two results in proving the continuity of proving the integrability of continuous function and discontinuous functions which are bounded. So in this next we discuss integrability of continuous function. We assume f is a continuous function and defined on a closed interval ab. We may take this interval a is not equal to b. If you take this a equal to b, then it will be a point, and what we have to do here for continuous function, so we take a is not equal to b, f is a continuous function on this interval. So as we have discussed, there can be taken a partition and its subinterval, and function, because of continuity, function will attain its bound at least once in each subinterval. So therefore the least upper bound of f and the greatest lower bound of f can be assigned corresponding to some value of ui vi in the subinterval xi minus 1 xi. So we have taken mi equal f of ui, mi equal f of vi due to continuity of the function. Now after assigning these values mi corresponding to ui and small mi corresponding to vi, the difference of upper sum and lower sum can be written as f of ui minus f of vi into, this is difference, delta I. So we wish to show this is less than epsilon, however small. When we take epsilon is greater than 0, be a given real number. So for improving integrability, we will prove this is less than epsilon. So let's see how we do that. Let epsilon greater than 0 be given. So by the continuity of f, there exists a delta greater than 0 such that the difference of these values f of u minus f of v will be less than epsilon upon b minus a whenever u minus v less than delta, the difference of these two values for any uv belongs to ab. So this point should be noted that this is true for any points uv in ab, and if their difference is less than delta, then their images, the difference of their images can be made less than epsilon upon b minus a. We will use this fact now here in this expression. So we will consider subinterval. Now we can take partition P such that its norm is less than delta. So this is always possible to choose a partition whose norms can be made as small as we can. So we can take the norm of P less than delta, which delta we obtained here above due to the continuity of the function. Now when you take ui vi in this subinterval xi minus 1 xi any points, then their difference will be less than delta I, cannot exceed from the difference of the interval. And this because norm of P is the maximum amongst length amongst all the length of subintervals. So delta I less than equal norm of P, and norm of P we have taken less than delta. Now implying the condition of continuity, we get f of ui minus f of vi is less than epsilon upon b minus a. Therefore the difference we have seen above now turns to this inequality. This inequality, now we are replacing the larger value epsilon upon b minus a instead of this f of ui minus vi, and as we replace this value we get this inequality which is a greater value, and this number inside the parenthesis is also b minus a. So b minus a is non-zero quantity and cancel with it. So upper sum minus lower sum can be made less than epsilon. So there is a partition P with a norm less than delta, for which the difference of upper sum and lower sum can be made less than epsilon, and therefore we have f is integrable due to our previous results we discussed. So we can conclude that if f is a continuous function defined on a closed interval ab, then f is integrable also. Now we will see that some function which are not continuous still integrable. So we will check how this can be done. So let f be a function having finite number of discontinuous point in this interval AB, and these points can be taken as a1, a2, ar, r points lying in this interval AB domain of the function, and their discontinuity find of f. Let epsilon greater than 0 be given. Now we can take a partition here which encloses all these points inside subintervals. In this way, I explain here. We this is a real line, and AB, this is the interval on this real line. So we can partition this real line. This is important to note, because the whole proof depend upon this partition. Okay, so students need to see all these carefully. Okay, so this is a real line and AB is just interval on it. So if you take points, we do partition of AB in such a way. We take a x1 y1 point in such a way, x2 y2, xi yi, xr yi. This is, so there are 2l plus 1 points total here. You can see here each, this is L, so there are points. Now we see this is a partition of AB. Now we see there x1 y1 is a subinterval, and there are finite number of points where function is discontinuous. So we can take first point here in this x1 y1, between x1 somewhere, x1 y1, x2 y2, e2, and ei is in xi yi between somewhere, and ar is here, xr yr, and we have taken a partition P which encloses these points of discontinuity. So now we make a wise step here. We can take the length of this all subintervals which encloses these points E1, E2, AR, such that we can consider partition P here, such that the total length of these subinterval enclosing the points of discontinuity, means x1 y1, you can see here in green lines. So the total length of these subinterval enclosing the point of discontinuity is less than epsilon upon 2 into m minus m plus 1, where capital M and small m are well known. So in this situation we have two types of partition of this partition, subpartition of this partition P. One kind of partition encloses these points A1, A2, AR, and the sum of their length, the total length of their subintervals or sum of their length is however small, as we can do. So there is another kind of rest of subinterval ax1, y1, x2, and there are other yi, xi plus 1, and there are other subinterval also. In these subintervals function is continuous, and in next with green lines function is discontinuous. So we can divide this study in two parts. In order to prove f is integrable for this partition P, we need to show that the difference of their upper sum and lower sum is less than epsilon. Now, as we had discussed, there are two types of subintervals. One contains points of discontinuity and other has no point of discontinuity, means function are continuous. Function is continuous in each subinterval. So in this later case, function is continuous in each subinterval. Thus, we divide this proof into two parts, and we shall show that the contribution of these subinterval in individually less than epsilon by 2. So we discuss cases 2 here. In first case, f is continuous in each subinterval. As we have this is a1 x1, y1 x2, and in this way. So function is continuous in these each subinterval. So by the previous result, function is continuous, then there exists a partition p1, p2, pr plus 1. Function is integrable. So by definition of integrability, there exists a partition p1, p2, pr plus 1, such that the difference of upper sum and lower sum can be made however small. So we take here epsilon by 2, r plus 1, and it is true for every partition pi. Now the total contribution of all these subintervals to this sum difference cannot exceed from, because the total contribution is one's contribution is epsilon by 2, r plus 1. So total contribution of these subinterval in this difference will be less than epsilon upon 2r plus 1 into r plus 1. It is very simple association. We can see that the total contribution cannot be exceeds from epsilon by 2 in this oscillatory sum. This is the difference of UFP minus LFP. Note that this partition P is we have taken in on previous page. So the total contribution of all these partition to this upper sum and lower sum cannot exceed from epsilon by 2. This is simply by continuity, because function is continuous in each subinterval. Now in second case, f is bounded, so it will be bounded in each subinterval. So xi, yi, however it contains point of discontinuity, but function is bounded, so such that the difference of upper sum and lower sum cannot exceed m minus f. It is well known that the difference of upper sum and lower sum cannot exceed from the this difference for each partition. Therefore, the total contribution of the subinterval to the difference this cannot exceed from, as this we have taken already, this is the sum of the total sum of subintervals, and in each subinterval the contribution of function cannot exceed from this upper sum lower sum. So therefore the total contribution of these type of partition to this difference cannot exceed from epsilon by 2. So by adding these two, contribution to UFP minus LFP, we get that the following result, means total contribution of these two types of subinterval, which makes a complete partition P, cannot exceed from epsilon. So UFP minus LFP is less than epsilon for the partition P here. So we have this result, a bounded function defined on a closed interval with finite number of points of discontinuity. Note that with finite number of points of discontinuity on the interval is Riemann integrable. Now what happened if the number of discontinuous points are infinite, but the set of limit points of the points of discontinuity is finite? Then we can show that still we will prove that difference of upper sum minus lower sum can be made however small, in the same way as discussed in the previous result, by considering a partition P in AB with a finite number of limit points can be enclosed in a finite subintervals. In previous result we enclosed point of discontinuity. Now we are enclosing the finite limit points. So finite limit points, as we know that in the neighborhood of limit points there are infinite many limits points except finite number of points. So we can divide a partition P in such a way that as I showed previous in the previous graph. Now you can consider A1 is a limit point, A2 is a limit point, AI, AR are limit points of the set of point of discontinuity. And now this interval contains infinite many limit points. However, the rest of part contains only either no point of discontinuity, no point of discontinuity, or finite number of point of discontinuity. However, this interval contains infinite many point of discontinuity with limit point a1. In same way, y1 x2 contains or either no point of discontinuity or finite number of point of discontinuity, and this interval contains infinite number of points of discontinuity with the limit point a2. In the same way we can write, so a1, a2, ar are limit points of the set of points of discontinuity. And in the same manner as we completed this result, the length of these subinterval can be made however small, and oscillatory sum of these subinterval cannot exceed m minus m, as we discussed in second case. And this is ax1 contains finite number of points where function discontinuous. So using the integrability, thus integrable conditions for discontinuous function can be achieved in case when function has infinite many points of discontinuity but having finite number of limit points. This description can be can be made in the same way as we discussed for discontinuity function part first. So we can conclude that if bounded function defined on a closed interval with finite number of limit points of the set of points of discontinuity of the interval is Riemann integrable. These are the books. Okay, thank you.